All right, so in this video, we're just going to work a few more examples with the Lagrange multipliers. And the first problem we're going to take a look at is to find points on this surface closest to the origin. And so they haven't directly told us what we need, but it's easy to put together a format similar to the previous problems. For us, we are going to minimize distance, which d equals the root x squared plus y squared plus z squared. Now, I know this information because we're trying to be closest, so we're minimizing the distance. And since it's the origin, the distance to the origin is going to be technically an x minus 0 squared, y minus 0 squared, and z minus 0 squared, since the origin is 0, 0, 0. So that's going to be our distance. And then it's going to be subject to the constraint, which would be g of x, y, z equaling xy minus z squared minus 1 equals 0. So if you guys remember a little bit of Calc 1, if our function here that we're trying to optimize has this square root above it, removing the square root is still going to allow it to optimize in the same place. That was an emphasis that I made early in Calc 1 that we've continued with throughout the sequence, but I will take advantage of it here as well. These two functions are not the same thing, but they will optimize at the same place. Okay, so let's go ahead and get our Lagrange equation set up. So we're going to have a 2x, a 2y, and a 2z. So that's the gradient of f. Going to be set equal to the lambda times the gradient of g. So this would be a y, an x, and a negative 2z for that gradient. So then our system will look something like this. 2x equals lambda y, 2y equals lambda x, and 2z equals negative 2 lambda z. All right, so in deciding where we want to go next, one of the first things that jumps out at me in a problem like this is this third equation. We have a z and we have a z. And so the question is, can we divide by z and therefore solve for lambda? Well, we don't know yet. And so what I'll do is I'll actually try it. I'm going to come over here to the side and I'm going to say, all right, for a second here, let's assume z does not equal 0. If z does not equal 0, then I can divide it off and I can easily say that lambda would have to equal negative 1. So if that's the case, lambda equals negative 1. If I take that lambda equaling negative 1 and I go back up here into these, I'll get a 2x equals negative y, and I'll get a 2y equals negative x. When I solve this system, it's pretty clear that it would give us an x equals 0 and a y equals 0. So if I take those x's and y's and go back into the constraint, I would get a g of 0, 0, z. Remember, z is non-zero, but x and y end up being. And in solving this now, when I plug my 0 in for x and y, I'm going to get a z squared equals negative 1. And that's not real. Since that's not real, that's not an option. That must imply that z is in fact 0. Okay, so we're able to conclude from contradiction that z is in fact 0. So let me go ahead and scoot the screen up a little bit here. And now we'll move forward under the impression, of course, that z is 0. So if z is 0, then both x and y can't be 0. I know that because up here, if z is 0 and I move the 1 back over, now all of a sudden x and y can't both be 0, otherwise, or neither one of them can be 0 for that matter, because if I have a 1 over here, something times something equaling 1 implies that these aren't 0. So we know that x's and y's aren't 0. So therefore, I'm going to come back up here and do a little dividing. Okay, I'm going to solve each of these for lambda, dividing by x and y, since again they're not 0. So this will give me a lambda equals 2x over y, and a lambda equals 2y over x. Now I can set both of these equal to each other, and I can solve. x squared is going to equal y squared. In other words, x is going to equal plus or minus y. Now we have to be a little bit careful here because there are two possible outcomes. There's the outcome where we need to consider g of x0 as well as g of x negative x0. Remember, if x is what it is, x could equal positive y, therefore x could equal, or y could equal positive x, or x could equal negative y, therefore I have my negative x here. So I have two possible things to consider coming from this plus or minus. All right, so for this first one here, I'm going to simply take my constraint. Every place I see an x, I'll leave it an x. Every place I see a y, I'll leave it a y. When I plug that stuff in there, that gives me an x squared equals 1, or an x equals plus or minus 1. There's no issue with that because if x equals plus or minus 1, then y would also equal plus or minus 1. Now, when it comes to x negative x0, again, I'm going back into this guy right here. So substitute or leave the x's alone. Let the y equal negative x. Z is going to equal 0. In doing that, we end up with negative x squared equals 1. Well, that's also not real. So that guy's going to get thrown out as well. So it looks like the only possible options we had came from this right here. So we would have then as our final answer f of plus or minus 1, 0. Remember, z is equal to 0. When you plug that stuff in back up here to the top, that this guy right here, that's going to give us the value of 2. And so that is the minimum distance from this guy right here to the origin. And remember, again, I put these points right here. Notice the pluses and minuses aren't going to matter with where I put them right here. So that's going to give us our value of 2. Okay, so now we're ready to talk about Lagrange multipliers with two different constraints. So the two different constraints that we're talking about might be something to the effect of g of x, y, z equaling 0. That would have been the first one we've seen. But now an additional one might be a y of x, y, z equaling 0. And so if this is the case, we're actually going to have multiple multipliers. And so we've got lambda gradient g plus the Greek letter mu gradient h. So we're going to have to combine now an additional one there. Here's your scalar multiplier right here, the Greek letter mu. So we still have our lambda, we now have a Greek letter mu. So let me go ahead and clear the screen here, and we'll take a look at an example using these two different constraints. Okay, so we are going to be looking at this function right here, subject to these constraints right here. Now, once again, I would probably go ahead and rewrite these. This guy I might call g of x, y, z equals x squared plus y squared minus 1 equals 0. And then the other one, h of x, y, z, would be a 2x plus a 2y plus a z minus 5 equals 0. Now, to set up the Lagrange equation, the gradient of f might be one of the easier ones we've ever done, 0, 0, 1. And then the gradient of g would be a 2x, a 2y, and a 0. Now we have plus mu, the gradient of h. So that'll be a 2, 2, and a 1 for that one. So 2, 2, 1. So you can see the setup's not really different, but as we move into the system, it will have an additional component that we need to consider. So 0 equals 2 lambda x plus 2 mu. 0 equals 2 lambda y plus 2 mu. And then fortunately, 1 equals mu. So when we look at this system, right off the bat, we know that mu equals 1. And so if mu equals 1 and I plug it in here and here, that's going to allow me to simplify these pretty quickly. In fact, when I plug those in, that's going to say that lambda x equals negative 1 and lambda y also equals negative 1. Now, the next logical step would be to go ahead and set these two things equal to one another. So that would say that lambda x equals lambda y, in hopes of being able to divide off that lambda. Now, the only way to divide off that lambda is to convince ourselves that lambda is not equal to 0. And so to investigate this, I'd probably come back maybe to one of these equations, or you could come up here if you really wanted to, but these are the same. So let's suppose lambda is 0. If lambda is 0, then this whole part right here, this whole term is 0, which means that 0 equals 2 mu, but mu equals 1. So that would say 0 equals 2, and that's not the case. Therefore, we can definitively conclude that lambda is, in fact, not 0. Since it's not 0, we can come over here and divide it off and come to the conclusion that x has to equal y. Since x equals y, I'm going to now come back into both of these constraints. So the first one would look like this. G of xx(z) would be x squared plus x squared equals 1, and h of xx(z) would equal 4x plus z equals 5. Now, conveniently, in this particular problem here, we're not going to have too difficult of a system to solve because this is already a single variable equation. When I solve this for x, we find out x equals plus or minus 1 over root 2. And so when I take that value now and I come down in here, that's going to give me a couple different z values. It's going to give me a z equals 5 plus or minus 4 over root 2, which if you really wanted to simplify, I suppose you could, into 5 plus or minus 2 root 2. So if we're trying to find the maximum and minimum, I'll go ahead then and say that f of 1 over root 2, 5 minus 2 root 2 is something to look forward to. And then f of negative 1 over root 2, negative 1 over root 2, and 5 plus 2 root 2 is the other thing that we would have to compute. So when it comes to z, fortunately, the function is very simple, right? It's actually just going to equal z itself. So when I conclude that 5 minus 2 root 2 and 5 plus 2 root 2 are the maxes and mins, this guy clearly being the min and this guy clearly being the max, it's going to then be subject to both of these constraints that we started with. Now, as kind of a summary to this problem, I want to circle back and make sure that everybody's seeing we really didn't do anything different. We had two constraints, so we had to have this additional plus mu gradient of h. We still had our system. For the most part, expect these systems to work out nicely. Otherwise, this would not be a very fair question. We do have to work through a little bit of logic, though, here with this lambda not being equal to 0. So that might be something to consider in the process of solving. But either way, once you come up with this idea that x equals y, or whatever it might be for your problem, you're going back into the constraints just like we did in the previous problems. This could potentially be another system. It worked out nicely in this case where we just went ahead and substituted directly in to come up with our z's. And putting it all together, the function itself was relatively straightforward, so we were able to identify the max and the min without a lot of effort.